I want to talk now about some of the fundamental relationships between the saturated conductivity and the fluid and media characteristics. And so our basic expression here is that the saturated conductivity can be described by an intrinsic permeability and a set of fluid properties. So the intrinsic permeability given by this kappa has units of length squared. And so you'll often see the conductivity of a medium described by its intrinsic permeability, which will have units of length squared. And what's nice here is that we do an experiment to get the saturated conductivity, for example. We get that value, but the question is, how would we translate that to a different fluid or a different media? Well, what we have here then is for the same media, if we change the density of the fluid or if we change the viscosity of the fluid, so this is the viscosity, and this is the density. If we change either the density or viscosity of the fluids, we could get a new value of the saturated conductivity. So for example, suppose we have some oil. And so we have our Ks for water is equal to the intrinsic permeability times the density for water and gravity, which is a universal, and then the viscosity of water. Now, if we solve this for kappa, we see that kappa is equal to the viscosity of water times K sat of water divided by rho of water, G, and that's it. Okay, so we have eta to rho G, excellent. Now, we know that this kappa, which is a function of the media, will be the same if we do the experiment in water or oil. So now let's go ahead and put the properties of the oil in there, the K sat for the oil phase, and the rho of the oil, and of course G still being G. Now, since it's the same media, it'll have the saturated conductivity for oil, the saturated conductivity for water. What we can do now is solve for the saturated conductivity of the oil, and we can say K sat of oil is equal to the viscosity of the water divided by the viscosity of the oil times the density of the oil divided by the density of water, and then times the K sat of the water. We notice that the G's cancel out. Okay, so what we can do then is by recognizing that the intrinsic permeability is a function of the media alone, if we're only changing the properties of the liquid, we can now exactly scale for the impact of those changes in the liquid phase to the new value of the saturated conductivity. But this is very useful, but it does not tell us what happens if we, for instance, compress the medium. So what happens if we change the porosity, for example? So that's when we use something like the Kozeny-Carman equation, and it lists some really interesting pieces. Here, N is the porosity of the media, and it shows up twice here. Since the porosity is typically far less than 1, this term is not as influential as this term. The cube term in the numerator is really dominant. And this is the tortuosity. And the tortuosity speaks to how much the path of water flow has to go around grains in the media. So if you have a highly tortuous path, then tau is big. If you have a very direct path, tau is small. Okay, so that's the tortuosity. So here now we can see, and then we have a kind of a geometric term to correct for whatever the geometry of the particular grains are. But basically, if we take a particular media and compress it, reducing N, we can see that the intrinsic permeability goes down to the third power, essentially, of that compression. And so oftentimes it's expressed as a formation factor in the denominator and the porosity in the numerator. Okay? So if you go and have a cup of espresso, you'll notice that the barista is going to pack the grounds, and by reducing the porosity significantly, they really reduce the permeability, which means that the grounds have plenty of time to get the nice strong coffee you're looking for. And so here we finally explained a cup of coffee for you. Now, Raviel and Cathels came up with another expression which is actually quite predictive. Again, it has the porosity to the third power, but now they put in a little variable that relates to the media itself, a value m, which goes from 1.5 to 2. And you can see that their porosity effect is even larger than that predicted here in Kozeny-Carman. And here we see that they have instead of having a constant for the medium, they actually now base it on the pore size of or the grain size of the media. So that's the grain size. And so the cool thing is we can now put together a picture of how the intrinsic permeability is a function of the grain size of the media, the porosity of the pack you have for the media, and then a simple geometric term in the 24 in the denominator. So fundamentally what we have is our set of expressions which put fluid and solid together and give us the approximate relationships between the media characteristics and the fluid characteristics.